All right, good morning, everybody. Before we get into the stuff today, there's a couple things I want to talk about. We are going to cover a few examples on the board with E1 and E2 elimination reactions on alkyl halides. So we'll do that. But also, next Wednesday is exam 2. So that's coming up. I will not be here on Wednesday, so there will be somebody in here administering the exam for me. And I'll be thinking about you while I'm in Puerto Rico. So I got a conference I got to go to, and it's in Puerto Rico. So.
Oh, I didn't know if you were just going on vacation.
No, I would not go on vacation in the middle of semester. It's business related. But I will be thinking about you while I'm having my drink on the beach, which ties us into alcohols today. So review sessions. This is what I'm thinking about. Saturday, with it being the football game, probably not going to work out too well.
Yeah.
All right, so I'm willing to come in on Sunday afternoon if that works for you, and I'm also willing to do Monday evening, and I'm willing to do both. So my wife has to work until about 7:45 on Monday evenings to teach her lab, so we could try to find a room, say 5 o'clock, 5:30, whatever, and have it come and go to answer any questions on Monday evening for about an hour, hour and a half, and then on Sunday afternoon, probably around 3, give you all time to do whatever you do on Sundays, get your dinners done, and do that as well. Does that sound like an okay plan? All right, I'll send out more details through Canvas. And you can come to both of them if you want. But anyway, all right. So last time we needed to talk about some examples of E1 and E2, right? So E1 stands for what? Yeah, elimination unimolecular. So what are we eliminating? We're going to take an alkyl halide, but what are we eliminating from the alkyl halide?
Hydrogen and the halide group.
Okay. Yeah, we're eliminating a proton and whatever X is, right? So we're eliminating HX from an alkyl halide to get an alkene. Exactly the opposite of what we learned in a previous chapter of taking an alkene plus HX to make an alkyl halide, right? And there's 2 ways for this to occur. And it turns out that E1 elimination mechanisms work really well for secondary and tertiary alkyl halides, okay? And X, chlorine, bromine, and iodine. And as you might imagine, as we go down the family, the leaving group gets better, right? So alkyl iodides should eliminate faster than alkyl bromides, should eliminate faster than alkyl chlorides, right? And so, so if we started off with, this 2-halobutane, whatever the halogen is, we can eliminate that in an E2 mechanism, or excuse me, an E1 mechanism by using some base and heating it. Usually these elimination reactions require a little heat, okay? Now, this is a beta elimination reaction. So we have to look at the alpha and beta carbon. So the carbon bearing the halogen, what do we call that?
Alpha.
That's alpha, right? And in this case we have beta, and I'm just going to call it beta prime. Beta 1, you can name it A, B, whatever you want to name it, okay? Doesn't matter to me. So there are 2 possible products from this elimination.
Yeah.
Which one is going to be the major product? The one on the top or the one on the bottom?
One on the bottom.
That's right, and why? Whose rule?
Zaitsev's.
Zaitsev's rule. Zaitsev with a Z, and don't ask me to spell it, Z-A-I-T-S-E-V, I believe. Zaitsev's rule states that you're going to get the most substituted alkene. right? Really what it states is that the beta carbon with the least number of hydrogens loses the hydrogen, right? But what that does is it gives us the most substituted alkene. Okay, and so here we have a disubstituted alkene, and so that's the more stable product. That is the product of this beta elimination reaction, okay? That's going to be the major product, okay? So this is going to be major, this is going to be minor, and in this case, you're probably going to see, you know, I'm not going to ask you to estimate what the ratio is going to be on a test, okay? But you need to know what the major is going to be. The major is going to be the most stable, right? But you're probably going to get this about 15 to 1, maybe 20 to 1, something like that, major to minor. So it's pretty good in terms of giving you the one product. Okay? But that doesn't tell us anything about the mechanism, does it? The same holds true for an E2 reaction. Okay? So how do I know that this goes through an E1 mechanism? Well, I got to look at the base, and I got to look at the conditions. And if the base is a fairly weak bases favor E1 elimination. Polar protic solvents favor E1 elimination. Okay? Why is that? Because it goes through a carbocation intermediate. So if the base happened to be, in this case, let's just say I do water. Water can also function as a base, but it's a bad base. So I take this alkyl halide, I put it in some water, and I heat it to boil the water, and I get the elimination to occur. How does the reaction happen? Well, this is a poor base. It's not going to abstract one of the hydrogens, but what's going to happen is, as we heat it, is the leaving group's going to leave. I'm going to end up with a secondary carbocation, right? And now what can happen?
And then the H2O attaches.
Yeah, so I've got hydrogens here, right?
Yeah.
So I'm just going to show you the major product. So I'm looking at the beta carbon that has the least number of hydrogens. And so now the water is going to function as a base.
Attacks the hydrogen.
It does. It attacks the hydrogen, and it gives me the product plus H3O plus X minus. That's the reaction. Okay? That's the reaction mechanism here. Now, why didn't water attack the carbocation? If water attacked the carbocation, I'd get an alcohol. Didn't I tell you all we could do SN1 too?
Is this not a strong nucleophile?
But I showed you examples of where we can take a carbocation, an alkyl halide, react it with water, and get an alcohol, right? It turns out that E1 reactions always compete with SN1 reactions. SN1 and E1 always compete with each other. You always end up with, bless you, okay? A mixture of stuff, okay? So how do I favor the elimination over the substitution? It's the reaction conditions. Heating a reaction almost always favors elimination. So if I heated this to, well, the boiling point of water is 100 degrees Celsius, I would know by the fact that I'm using a lot of heat that the elimination pathway should be favored. Now, if I ran this reaction at 35 degrees, what would I predict the major product to be? The alcohol, the SN1 reaction. That's the terrible thing about E1 and SN1. They always compete with each other. Okay? So when you talk to chemists, they typically don't like E1 and SN1 type chemistry. Okay? Unless it's under special circumstances where you can only get one product. Okay? E1 will work for secondary and tertiary alkyl halides only. It will not work for primary. Why is that?
Can't form a carbocation.
A primary carbocation is too unstable. Primary alkyl halide can only do E2. Okay? Secondary and tertiary, however, can do E1. Tertiary can only do E1 when you have a poor base. Okay? Poor base, not a good base. Okay? Things will be a little bit different there. Okay? So that's the E1 elimination pathway. What do we have to pay attention to? Carbocation rearrangements. Okay? Got to be very careful about carbocation rearrangements. So let's look at an example of an E1 elimination. Let's say you take let's make it bromide. And let's say Jason takes this, places it in a poor base, water, whatever, heats it up. What's the product going to be of that elimination reaction?
Is it a strong base or a
Weak base, weak base. So we're under, I'm telling you right now, we're under E1 elimination condition. Okay?
Is it gonna be 1, 2 cyclohexene?
Tell me,
Yeah.
work through it.
Oh.
So right.
Yeah, work through it. You all are gonna guide me through the mechanism. Yeah,
What does the triangle mean?
heat. I'm sorry, heat. Heat it up.
So the bromine will detach first, making a carbocation.
Okay, and we know that because we're in a polar protic solvent. I've told you we've got a weak base, right? So the rate determining step, right, is going to be the leaving group leaves. I end up with what kind of carbocation?
Secondary.
That is a secondary carbocation. So I do what? I stop and think about it, right? Can that rearrange to a more stable carbocation?
Yeah.
Well, if it rearranges here, it gives me a secondary, so that's not good. But if this moves, now I can get a tertiary carbocation, right?
Yeah.
And I always use a little curly Q error to indicate rearrangement. And so since this carbon with its electrons moved here, that puts the carbocation there, right? So now I have a tertiary carbocation, which cannot rearrange to a more stable carbocation. So now what happens?
The weak base.
Yeah, but I actually have the possibility of getting three products here. I've got beta, beta prime, and beta double prime.
Oh. Yeah.
Beta, beta prime, beta double prime.
So we need to see how many hydrogens each beta.
All right, so how many hydrogens are on this beta carbon?
3,
3. How many are on this beta carbon?
2,
How many are on this beta carbon?
1.
Which one's going to lose it?
The 1.
That one, right? And so the base will come in, extract the hydrogen, and so I end up with that as my organic product. Okay? So not only do you have to worry, just one second, not only do you have to worry about E1 and SN1 competing with each other, but you also have to worry about rearrangements.
How do you determine your betas?
Okay, so this was my alpha, right? So that means that this carbon would be alpha because it just lost the halogen, right? And so basically anything that's attached, and then it rearranged, right? So now this is the carbon bearing the carbocation. So now this is my alpha, right? And anything that's attached to that has to be beta.
Okay.
Does that make sense?
Thank you.
The rearrangement actually did make for a different alpha carbon, didn't it? Okay? So you got to pay attention to that. So that's E1.
Can we do another example?
Yeah,
Can you go forward to another example like we did now?
yeah, I can throw another one up.
Is there any chance you can show us an example of when the carbocation rearrangement only move a hydrogen instead of like a whole methyl group?
Yeah, I can.
Yeah, like you just.
Let's see, let's do this. So let's take. Let's pick on bromine again. Weak base, say water, heat it up. What's the product gonna be? Heat it up.
The bromine leaves.
Okay, we know it's gonna be an E1 because it's secondary.
Yeah.
Poor base, polar protic solvent.
Yeah.
Leaving group leaves. Okay. Now what can happen? If the methyl group moves, I just end up with another secondary carbocation.
Yeah.
That's no better,
Yeah.
right? But I also have a hydrogen here, right?
Yeah.
So if that hydrogen migrates,
Ah. That makes sense.
then I would get, there's my hydrogen, right? There was already a hydrogen there. So that's why there's two, not two moved. There was already one there. And now I end up with what kind of carbocation?
Tertiary.
Tertiary.
That's better.
That's better, right? And now I eliminate from either here or here, doesn't matter which. And I end up with my alkene product. That's the major.
Would you give us something where we have to rearrange a hydrogen?
I just did.
No,
On a test?
yeah.
It's possible, yeah. That's fair game.
Can you do one exactly?
Can I do one exactly like that?
Yeah, it's gonna be one.
Now, that wouldn't be a good test, would it?
Well, it's only gonna help.
So, from what we learned, what do we know about E1? We know that E1, we know that alkyl iodides will eliminate better than bromides, will eliminate better than chlorides for E1, right? I know that tertiary alkyl halides are going to react faster than secondary alkyl halides, right? And I know that poor bases favor the E1, and I know that polar protic solvents favor E1. Okay, that's what I know. And we just did some examples. Now let's talk about E2. Oh wait, excuse me. And that the rate is proportional to the concentration of the alkyl halide. Okay? That's the only thing that comes into the rate. So if I want to speed the rate up, I better add more alkyl halide. Cool.
Are you gonna tell us on the test if it's like a poor base or something?
So poor bases are typically bases that aren't charged. They have a low pKa value. So I would give you some way of knowing that, yeah. Yeah.
Okay, this may make me sound stupid, but I'm not too familiar with carbocations anymore. Can you just like go over how to determine the difference between primary, secondary, and tertiary again?
The number of carbons that are attached to it.
One.
So a primary carbocation would be that. So the carbocation has one carbon attached to it?
Primary has one.
Yep.
Secondary has two.
Yep.
Tertiary has three.
Yeah.
So a secondary would have two carbons attached to it, and a tertiary would have three carbons attached to it. Tertiary are more stable than secondary. Primary, for all practical purposes, doesn't exist.
When someone said those things, I just saw the images of like in live pop up in my head.
Oh, good.
I was like, oh wait, I know what that is.
The E2 elimination mechanism a little different. Like the SN2, the rate is going to be dependent both on the concentration of the base and on the alkyl halide. The bases in this and E2 eliminations are almost always charged bases. Hydroxide, alkoxide, tert-butoxide, those types of things that your book talks about, okay? So if we take an example, again, of this alkyl halide where X can be iodide, bromide, or chloride, doesn't really matter, and I use something like potassium tert-butoxide as a common base that gets used. Okay, it's just oxygen with a negative charge that's attached to a tert-butyl group. Okay, it's the potassium salt usually. Okay, and if I run this reaction again, I have the possibility of ending up with two products. Which one's going to be the major product? Zaitsev's rule, right? Zaitsev's rule works pretty well. But what I would notice if I ran this reaction, if I doubled the amount of potassium tert-butoxide, the reaction rate would double. So the base is important in the reaction. And so what happens, again, to follow Zaitsev's rule, it means we're going to take it from the beta carbon with the least number of hydrogens. Of course, there are 2 here. There are 3 there. The base removes the hydrogen. Those electrons in the carbon-hydrogen bond come over to form the double bond, and the leaving group leaves, all at the same time. That's why the rate is dependent on both species. It's one step. Okay? Primary alkyl halides can only eliminate by an E2 mechanism. All right, so if I took bromopropane, 1 bromopropane, and I reacted that with my potassium tert-butoxide, I would end up with my product. In this case, I've only got one product, right? That happens by an E2 mechanism. Because I can't generate a primary carbocation, I can actually take that alkyl halide, put it in water, and boil it, and it will just stare at me. Won't do anything. It won't eliminate. Okay? E2 elimination reactions typically occur at lower temperatures. You typically don't have to heat them. Okay? You typically don't have to heat them.
Could you go through the mechanism of the bromine one? Just
This one?
Draw the arrows for us.
Sure. So there's my beta carbon, right?
Yeah.
The trick here is you need what we call a non-nucleophilic base. Non-nucleophilic. It does not behave as a nucleophile. That's why you will typically see people using things like potassium tert-butoxide. Why is potassium tert-butoxide not a good nucleophile? Because this T-butyl group is actually pretty big. And it shields the oxygen. So if the oxygen tried to attack the carbon, the big stuff on the tert-butyl group and the alkyl stuff hanging off of the alkyl halide would start to run into one another. It can't get to the carbon very easily, but it can pluck off a hydrogen because hydrogen is small. Okay? So you need things like non-nucleophilic bases to do this. And this is the common go-to. There are probably a dozen non-nucleophilic bases that if you were taking my Chemistry 255 class, you'd have to learn. For this class, you only have to learn potassium tert-butoxide. It's good enough. Okay? So this is a non-nucleophilic base. What would happen if we used let's say sodium hydroxide. What could happen here?
It's a strong nucleophile.
It's not a bad nucleophile, and it's also not a bad base. So what can happen?
Compete, maybe.
We can get competition. So you can actually get both products. If I run this reaction at room temperature-ish or lower, what product do you think predominates? The substitution or the elimination? Substitution. So, low temp favors substitution. Well, let's say Jason takes the reaction, he mixes all these things together, and he starts boiling it. What's going to be the major product? Elimination. So this will be the major product at higher temperatures. Okay?
So X is OH, or what's X?
X could be chlorine or bromine or iodine.
Okay. So low temperature place, and when it gets boiling, it goes away.
Yep. Two possible pathways, right? So what do I know about E2 reactions? I know that tertiary react faster than secondary, reacts faster than primary. Why is that? If you think about a tertiary alkyl halide, it's got 3 beta carbons, all of them with hydrogens usually, right? So it's a lot faster for that to occur, right? The odds of the base running into a proton are greater. Okay. Primary still works. I mean, there's no problem with it. It's just you've only got 1 beta carbon to eliminate a hydrogen from, so it usually goes a little bit slower. I know that iodides are much faster than bromides, or much faster than chlorides. I know that the rate of the reaction is proportional to both the concentration of the alkyl halide and the concentration of the base. I know that low temperatures favors SN2. High temperatures favor E2. Okay. And it matters. I've had students come into my lab do research. We have a little thing called a rotovap that helps remove solvent. It's got a water bath to heat, boil off the solvent, does it under vacuum. They crank it up, get it really hot, and then they get the product they don't want. They eliminate it, as opposed to doing the substitution chemistry.
So high temperature favors E2,
It does.
and high temperature also favors E1.
It does. Just think about it, if you want to just compartmentalize it, higher temperature favor elimination. Okay.
So what we need a strong base for E2?
You do. You need a stronger base for E2. You need something that's negatively charged. Alkoxides like potassium terpetoxide, hydroxide. They can all do E2 eliminations.
Then do we also need a polar aprotic solvent, or is it still polar aprotic solvent?
These are done in polar aprotic.
So these are polar aprotic
Yep.
for E2.
It favors the E2. Okay. Science is about relative arguments. And so when you're comparing the two, you have to look at all the considerations and make your best guess, your best determination, right? All right, so let's jump into chapter 8. So whatever we cover today and cover on Monday is fair game on the exam next Wednesday. The exam will be the same format that you saw last time. You'll get a zip grade form, okay? I will give you a copy of the periodic table. I will give you a list of pKa values if you need them. So don't worry about memorizing your pKa's per se. I'll give you a list. You can have your model kits My advice to you is to come in with your model kits pre-built.
What should we do about it?
So if you have the model kit like I am showing you, what I would do is I would have several carbons already put together so you're not wasting time. So when I went into my exams, when I had the model kit, I actually built a 6-membered ring and just connected it all together. And then I had a couple of other carbons that were put together in just a chain. And I had my spheres, and I was ready to go. I could disassemble anything I needed to and put together what I wanted pretty quick. You don't want to waste time on the exam snapping pieces together is what I'm telling you.
Can you write us a list real quick of models to build? Like, that would be helpful.
Well, I would just put the pieces, the carbon pieces together.
What do you mean put the carbon?
Your model kit's a little different.
Mine's a ball and stick model.
Yours is a ball and stick. And so what I would do in your case is I would actually come with the balls already having the sticks stuck in them. So you don't have to waste a bunch of time putting sticks in. I'd come with 4 or 5 of those already put together like that.
So just like carbon and with sticks attached to it?
Mhm. So that you can, more quickly assemble what you need. All right. So we are going to talk today about alcohols and ethers. Okay, we've already talked a little bit about alcohols, right? Alcohols have the OH functional group. We call that a hydroxyl group. So any carbon atom, right, attached to an OH, this is the hydroxyl. This would be an alcohol, okay? We can also have other kinds of alcohols. This is called an enol, where it's attached to what looks like an alkene. And we can also have molecules called phenols, which look like alcohols, but they're attached to these aromatic rings. And we're going to learn about aromatic rings in chapter 9, I think. So don't worry too much about it. I just want you to know that there are several different flavors of alcohol. We can have regular alcohols, we can have enols, and we can have phenols. And they all have that hydroxyl group.
Those are enols and those are phenols?
Enol, phenol, yep. Right? So there's an example, and actually an aromatic ring is abbreviated as AR, so that's what a phenol is. Okay? Now you all know several examples, right? This example, CH3CH2OH. Okay, this is beer, right? This is ethanol. Also known as ethyl alcohol. So there are systematic names and there are common names. I'm going to spend a little bit of time on nomenclature, but not a lot. Okay, there's just one real important rule about alcohols that you need to know, and everything else is the same in terms of naming. Okay? Anybody want to take a guess at what the name of that one would be? 2-propanol, yeah. It's also known as isopropyl alcohol. You all buy a 70% solution of this at Walmart or CVS. This is called rubbing alcohol. Okay. How would you name that one? Pardon? The one there in the blue. The one that doesn't have a name under it.
5.
It's got 5. So it's going to be a pentanol of some kind. What kind of pentanol?
Cyclo.
This is cyclopentanol, right? It's cyclopentane that has an OH. So it's cyclopentanol. Okay?
That was close.
You weren't far off. Yeah.
That's what I said.
Yeah. Ethers have the general structure of having an oxygen atom between 2 carbon atoms. That's an ether. Okay? That's an ether. Everybody always kind of likes this around Halloween because you put in the lone pairs. It's like a bat. Right? That's diethyl ether. It used to be used as an anesthetic. Right? Not a student. A patient would come in and need to be put to sleep to perform surgery. They would actually take cotton, soak it in diethyl ether, put it over the person's face and mouth, or nose and mouth, and they would eventually go into a state of anesthesia. We no longer use diethyl ether for that purpose. Anybody want to tell me why?
Is that what they do in movies when they have like try to kidnap someone and they put like a towel?
They probably in the movies would refer to that as chloroform. You can chloroform somebody else too, but yes, essentially that's what they're doing. Yeah, and it doesn't happen that fast. If it did. Anybody know why we don't use diethyl ether anymore as an anesthetic? Pardon? Just about any anesthetic could cause brain damage. I mean, if done not correctly. But
Is it because it's combustible?
it is combustible. Yeah, it's very, very flammable. So if you've ever been on a farm where they have a old diesel tractor, they will use diethyl ether and spray it in there to get it to start because it's combustible. So people literally were on the operating table being ethered and then caught on fire. And it's not a great way to wake up from your operation, right? So we no longer do it, okay? If you go into an organic lab, like if you were to come up to my lab, the odor that you might smell would actually be diethyl ether. We use a lot of diethyl ether to do a lot of extractions. It's one of the reasons I became an organic chemist. I really like the smell of diethyl ether. It's nice. Nice and relaxing. So here's some examples. Again, the oxygen atom can be attached to just about any kind of carbon, but it has to be attached to a carbon. All three of those examples are ethers, okay? So a couple of things that you need to know in terms of physical properties for alcohols in particular. Melting points and boiling points increase as the size of the R group increases. So, for example, on an exam, I could say CH3OH. I could ask you to rank those in order of increasing boiling point. Which one of those would you predict to have the lowest boiling point? The shortest one. So this would be the lowest boiling point, right? So you'd say that has a lower boiling point than which one? This one, right? And then that one would have the highest boiling point, right? So the more carbon atoms you have in the molecule, the heavier it gets. And not only the heavier that it gets, the more London dispersion forces that it has between each other. So you learned about that in Gen Chem, right? The ionic or non-bonding interactions. So as we get bigger, boiling points will increase. Alcohols are typically soluble in water up to a point, right? So if you go to the bar tonight and you order a mixed drink, you don't worry about the ethanol separating from the water that they pour in there. It looks homogeneous. That's because ethanol only has 2 carbons. You go and use your rubbing alcohol. I don't know, you got a cut or whatever. You don't worry about it not being soluble in water. It has 3 carbons. It's perfectly soluble in water.
Is that why you should leave alcohol bottles open?
You shouldn't leave alcohol bottles open because the alcohol also evaporates pretty easily.
Yeah.
You lose it to evaporation, or at least small alcohols. And also because as it evaporates, you get flammable vapors. And so one of the things that has been known to happen is somebody will have an alcohol bottle out in their, in their vanity area or whatever, and leave it open, and then they'll light a candle, and that makes for a bad day, really quick. So basically, your smallest alcohols up to 3 carbons, we say that those are completely soluble in water. You can take 100 milliliters of ethanol, you can take 100 milliliters of water, you can mix them together, and you get a little less than 200 milliliters of a drink. Okay? Alcohols, however, when you get up around C8, 8 carbons, you start to have limited solubility. Okay? So, things like methanol, ethanol, 1-propanol, 2-propanol, all of these things are going to be completely soluble in water. Okay? Butanol will be somewhat soluble in water. And then how many carbons do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So nonanol is not going to be soluble at all, right? And so what you find is that butanol, you can only get about 8 grams of the alcohol into 100 milliliters of aqueous solution. So it's about, by weight to volume, about 8%. Okay? This one, however, much less than a fraction of a gram will go into 100 milliliters. You will actually form 2 layers.
Oh, you mean like they'll separate, okay,
They'll separate, yep. I mean, I can mix them together, but I'll have 2 layers.
okay.
Yep.
But you're saying like you were gonna add it and then it wasn't gonna add, I was like, what?
No, it'll add, it just will separate. Yeah, you'll end up with 2 phases. Okay? And if you think about it, it makes sense. We know that like dissolves like. Alcohol kind of looks like water, but if I start putting a lot of carbon on it, it starts to look like grease. And we know that oil and water don't mix, right? So that kind of makes some sense to us there. There is a solubility rule of thumb that I tell all of my students. Okay? You need to know this rule of thumb, because it turns out what they told you is only partially true. The rule of thumb is that for every hydroxyl group, if you have 5 or fewer carbon atoms, it will have some solubility in water. Why is this important? Because there are polyols that you all take that are perfectly soluble in water that have lots of carbons. But when you look at the number of OHs relative to the number of carbons, it usually satisfies this 5-carbon rule. Okay?
Wait, can you say that again? For every hydroxyl group, if you have
5 or fewer carbons, typically you are going to be soluble in water. So for example, let's look at this. So let's say that Jason takes cyclohexanol. Would you predict that that would be highly soluble in water? No, I wouldn't predict. I would predict that if I put that in water, I'd get 2 phases. Would I get a little bit in there? Yeah, I'd get a little bit, probably around 5 or 6 grams, maybe, for 100 milliliters. But now, what's the ratio of OH to carbon here?
1 to 6.
Yeah, 1 to 6. It doesn't satisfy my 5-carbon rule. But now Jason adds 1 more hydroxyl. Now what's the ratio?
1 to 3.
2 to 6, which is
1 to 3.
1 to 3. That satisfies my 5-carbon rule. This, I would predict, would be completely soluble in water. Okay? Are there exceptions to this rule? Of course there are exceptions. We're not going to focus on those exceptions in this class, though. Okay? Just know the 5-carbon rule for your solubility. That's a rule of thumb. It is not a law. Okay? If you all have ever taken Miralax, it is a polyol that has a molecular weight that is huge. And it is perfectly soluble in water because the ratio of alcohols to carbon satisfies the 5-carbon rule. I forget what the ratio is, but it's perfectly soluble. You make a solution of it, you drink it, and then you wait a few hours and it does its job, okay? But it is a polyalcohol, okay? The physical properties of alcohols really do stem from the fact that the alcohol is kind of privileged in the sense that it can form hydrogen bonds. You all might remember what hydrogen bonds are from your time in general chemistry, right? A hydrogen bond is a bond between a hydrogen atom that is attached to something like oxygen and another oxygen. So here's an example, right? So methanol will hydrogen bond with itself. Another molecule of methanol will come in and form a hydrogen bond. What do we know about bonds? Do they release energy or do they take energy to make?
To make,
To make the bond.
energy takes energy.
To make the bond?
No,
To break the bond takes
Break
energy.
the bond.
To make the bond
releases energy.
releases energy. So is forming a hydrogen bond a good thing or a bad thing? It's a good thing.
Good.
It releases energy, right? Releases energy. And so alcohols like the hydrogen bond. These aren't permanent bonds. They're not covalent bonds. They're fairly weak, relatively speaking. They're a lot weaker than a covalent bond, but they're a real bond. Okay? And so what that means is that the alcohol has these kind of partial bonds with other alcohols, which impacts its physical properties. Alcohols have much greater boiling points than alkanes, even if they weigh the same, because of the hydrogen bond. Okay? So hydrogen bonding is very, very important. And it turns out that primary alcohols can hydrogen bond much better than secondary or tertiary alcohols, because the alcohols can get closer together and form that bond. A tertiary alcohol has all that other crap around it, right? Use the technical term, right? That gets in the way. And so you're going to find that hydrogen bonds between primary alcohols are actually quite strong. This is why alcohols are soluble in water, because the alcohol forms hydrogen bonds with water. Okay? Go home tonight and get some, especially if you have 91% isopropyl alcohol from Walmart, put a little bit in your hand and then add a drop or two of water and rub it, and you will feel the heat. Mixing alcohol and water actually generates heat because you're forming hydrogen bonds with the water. And all bond-making events release energy, right? Release heat.
Is it significant that if I put some alcohol in a cup and I put some water in it, am I gonna feel it?
You will feel it. It will not burn you, but if you put a thermometer in there, you'll see it go up a few degrees. Yep. You can definitely tell it very, very easily. Okay? And so here's an example. So if you look at all three of these molecules listed up there. Let me get my pointer out. And if you went through and did the math, okay, what's the name of this molecule? That's butane. What's its functional group? It's just a pure alkane, right? Okay. This is called methyl ethyl ether. Don't worry about that yet, right? But it's an ether functional group, right? Carbon, oxygen, carbon, right? It has about the same molecular weight as butane. And if you look at propanol, right? Again, it's an alcohol functional group. It's just an isomer of this, right? It has exactly the same molecular weight here. And what you're going to find, notice the physical properties. Butane boils at 0 degrees Celsius. This ether boils at 11 degrees. And this alcohol boils at 97, even though they all have about the same number of carbons. They all weigh about the same, but the functional group is different. Why? All this has is van der Waals interactions. Right? You learned about that in Gen Chem. We didn't talk too much about it here, but it's just van der Waals, very weak interactions. In fact, van der Waals interactions, if you'll remember, you may have gotten the example, that's how saran wrap sticks to itself. If you've ever had to fight with saran wrap, and it's, right? It's because of just van der Waals interactions are holding that together, okay? You just have billions and billions of van der Waals interactions on a big sheet of saran wrap. This ether, right? Because you now have the oxygen, it's polar, so you have dipoles. So you have, that's what DD means, is dipole-dipole interactions. It increases to the boiling point of about 11 degrees here. And now we have hydrogen bonding, which increases the boiling point to almost that of water, 97 degrees. Okay. You also notice here where we have isomers of the same alcohol. This is a tertiary alcohol, this is a secondary alcohol, this is a primary alcohol. Notice what's happening to the boiling point. Why is the boiling point increasing? Because I know that primary alcohols can hydrogen bond better than secondary alcohols can hydrogen bond better than tertiary alcohols. Okay, so the stronger the hydrogen bond, the higher the boiling point is going to be as well. And then there's that solubility rule of thumb. It also applies to ethers. Don't worry about the word epoxides yet. That's later in the chapter. But if you have 5 or less carbons per OH, right, you're going to have water solubility. Whoop. All right. Nomenclature of alcohols. Everything that you've learned about nomenclature so far works. The first thing you're going to do is you're going to identify the longest carbon chain. However, the rule changes for alcohols in that longest carbon chain must contain the OH. The parent chain contains the OH group. So if you have 2 of them that are 6 in length and one has the alcohol, one doesn't, you pick the one that has the alcohol. Okay? And you're going to number the parent chain to give the OH the lowest possible number. That is not true for other substituents. Remember, if it was a methyl group or a halogen, we just numbered, and halogen didn't take precedent over any other function or substituent, excuse me. OH, however, does take precedent. Okay?
So it's similar to alkene where we prioritize the double bond.
Similar to that, yeah. Yeah, certainly. And then there are some common names. Okay? So there are common names that come into place, like ethyl alcohol.
Ethyl and OH.
Yeah. Ethanol is the appropriate IUPAC name, but a lot of people call it ethyl alcohol. What's another common name for ethyl alcohol that you might be aware of? If you go around those moonshiners, they call it grain alcohol. Right? They take grains and they make alcohol illegally out in the woods, right? And make moonshine. So some old timers will call it grain alcohol. Methanol is the common name. Some people call it methyl alcohol. Okay? That's another common name. Old timers would call that wood alcohol. It's the kind of alcohol you get by trying to distill wood. It's poisonous, it's toxic.
It's the one that makes you go blind.
Pardon?
It's the one that makes you go blind.
It does. It does make you go blind. It will very, very easily. And we'll talk a little bit about that. All right, so break up into some groups for about, let's go for about 4 or 5 minutes. I want you to name those 4 alcohols. Is what 6?
The A, SH2.
Right here? That is a 6, yes. I would point here, but you'll see that the laser pointer doesn't work on television.
So, we're supposed to label these? Name these?
Name these. Yep. Name A, B, C, and D.
Good.
Tired.
Right. Jason, what do you think of what you got at?
Love it.
A.
For the second one,
What do you think about it?
Well,
would it still be
I'm
five,
counting C's
or
and
would it be
C's.
4
One, two,
without counting
three.
the OH?
Sure, 3?
You want the OH to have the lowest
Unless we
number.
always find 6.
Wait, I'm
Say that again?
Oh, we multiplying 6.
like, whenever you're first trying to find the parent
So
chain.
there's
Oh, you find the parent chain, you count, and you find the longest one that would be attached to the alcohol. So,
Like ending-
1, 2,
ending-
3, 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's gonna be 5, right? Yeah. All right. Let's answer the first two. These are actually in your book. The solutions are there. I'll post the other two, walk you through them step by step, but in the interest of time, we're only going to spend time on A and B. So what did you come up for A? What's the longest parent chain? Butte? How many carbons do we have in the longest chain? We have 8, right? We've got CH3, then we got 6 CH2s. 1, 2, 3, 4, 5, 6. Then we got CH2OH. Right? So what is that? Octanol. And what do we, can I just say octanol?
Octanol. No, wait, no, we didn't say hot today.
It's 1 octanol. The OH is on the number 1 carbon. Gotta say it, right? Because I could have 2 octanol, I could have 3 octanol, I could have 4 octanol. Can I have 5 octanol?
No.
No, because then it becomes 4 octanol, right? Gotta keep that in mind. All right, B, we've got right, so the longest chain has to be including the hydroxyl group, right? So that could be this, could be the longest chain, so that's what?
That's pentanol.
Pentanol.
Numbers? Question mark?
And we got a number, right? So am I going to number this way or this way?
This would.
This way.
I'm going to number to make the, so it's going to be 2 pentanol, right? And 4-methyl. So 4-methyl 2-pentanol is the correct name for that particular one. I will tell you that C has chiral centers. So you have to include in the name the R and the S, and I'll post that, okay?
Oh. Oh.
All right, so let's talk a little bit about some interesting alcohols. Of course, you all know about ethanol, right? This is where we get our wine, our beer, my Jack Daniels, all the stuff that I like to drink. Okay? This is what you would call an alcohol that we derive from fermentation, right? It's a biological process. You take some type of juice that contains a lot of sugar or some type of carbohydrate. You feed it yeast, or you feed that to yeast, and this is what yeast urinate out. So when you're drinking alcohol, you're literally drinking yeast urine, okay? And we seem to enjoy it, most folks, okay? It is a very simple alcohol. It is completely soluble in water, okay? Doesn't have much of a taste by itself. If you've ever drank Everclear, it can burn, but when you start mixing it with other things, and gets pretty flavorful. Okay, methanol. This is also known as wood alcohol. It is also a very simple alcohol. This used to be used as the alcohol as an antifreeze in car engines. They no longer use it because it actually turns out to be fairly corrosive to metal over time. It is also the alcohol that is used in your windshield wiper fluid. Usually contains methanol. Okay? They color it blue for a reason. Most people don't drink blue things, right? Powerade, I suppose so, yeah. But don't confuse this for Powerade, because as little as 15 milliliters of this will cause blindness, permanent blindness. And if you were to drink 100 milliliters of this, it would kill you. Okay? It's amazing. What's the difference between methanol and ethanol? 1 carbon. 1 carbon. 1 carbon you get at the bar. 1 less carbon, it kills you, right? And it turns out this is the thing that you have to pay attention to if you were to buy illicit liquor, because if they don't distill it correctly and they gave you what's called the heads contain a lot of methanol. So if they distilled that out and gave it to you to drink, you would go blind and you would die. Okay? So people need to know a little chemistry if they're going to do this kind of activity.
What if there was 1,000 ways to die?
Well, we don't need to go down that path.
I'm making jokes.
I know you are. 2-propanol, you all know about this. This is rubbing alcohol. And then this is ethylene glycol. What's special about it?
Glycol?
2 hydroxyl groups.
2 hydroxyl groups. Okay? Is that going to be soluble in water?
Yeah.
It's going to be very soluble in water. Okay? This is no longer the major component of your car's antifreeze. But the time that this slide was made, it was still used as antifreeze in your car. It was the green stuff that you would pour into your car. Today you pour pink stuff or orange stuff into your car. You actually use, instead of ethylene glycol, you use propylene glycol, which has 1 more carbon. The reason is because ethylene glycol is extremely sweet tasting. I've actually tasted it. Don't do that. It's as sweet as any sugar you've ever tasted. And a lot of children have died, and pets have died from ethylene glycol poisoning. So a shade tree mechanic goes out and changes their antifreeze. They drain it into a bucket. They set it aside. A dog comes along and licks it, and it's sweet. What do? They keep licking it, and they keep drinking it, and it will kill them. Okay? It is very, very toxic. Propylene glycol, again, 1 more carbon. Not toxic. Okay? Or less toxic. Let me put it to you that way. I'm not going to say so. But a lot less toxic. Here's some ethers. These are interesting ethers. These are called crown ethers. Notice it's not just 1 ether group. It's many ethers in a ring. Okay, these are called crown ethers. And these are actually used to separate salts from one another. So for example, potassium and lithium. If you think about going out to mine potassium and lithium, why would we be interested in mining lithium today? Batteries. Each and every one of your cell phones uses a lithium battery. If you depended on lead acid batteries, like your car battery, your phone would weigh like 7 pounds. All right, not very convenient. Lithium, much better battery technology. But everywhere you find lithium, for the most part, in nature, it's not pure lithium. You can't go to the mine and just say, here's pure lithium, right? It's lithium and sodium and potassium, and you have to find a way of separating the lithium ions from the other. We can do that through what's called complexation with these crown ethers. Lithium will fit, because lithium is small, it will fit into this so-called 12 crown 4. So if you treat your stuff with 12 crown 4, you can pull the lithium out. If you treat it with 18 crown 6, you can pull the potassium out. Okay? So these ethers do have a vital role to play in our mining operations today. And so it's a whole area of stuff called host-gas chemistry. We're not going to talk about it. I will say that Nobel Prizes have been given for this kind of thing, okay? Because it is industrially important to be able to separate lithium from other cations. And other cations. I mean, potassium is useful too, right? You already know several ways to make alcohols and ethers. You can just use SN2 chemistry. I can take a primary alkyl halide, I can react it with hydroxide as a nucleophile. What temperature would I need here? Low temperature or high temperature? I would probably do this at low temperature, right? Room temperature maybe, right? And I get an SN2 reaction and I get an alcohol. You could make synthetic ethanol this way. I could take ethyl bromide, react it with hydroxide, and I can make ethanol. It would be very expensive ethanol, but you can make ethanol.
Handmade ethanol.
Pardon?
Handmade ethanol.
Handmade ethanol. That's right. I much prefer the yeast to do it for me. You can also make ethers by using so-called alkoxides, which we learned a little bit about, right? Again, doing an SN2 reaction to give me an ether. This is called an unsymmetrical ether because notice it's a methyl group on this side and a propyl group on that side. We call those unsymmetrical ethers. Notice, however, if I take ethyl bromide and ethoxide and react them together, I get a symmetrical ether. And this is how you can make diethyl ether. That's one way to make diethyl ether in the laboratory. Making ethers this way, either way here, making symmetrical or unsymmetrical ethers is called the Williamson ether synthesis. One of the things that organic chemists are extremely notorious for is naming their reactions. If you were taking organic 255 or 256, I would require you to memorize named reactions because that's how we talk. You don't come into the lab and say, I want to react bromobutane with ethoxide to make an unsymmetrical ether. You say, I'm going to make an unsymmetrical ether using the Williamson ether synthesis. And everybody knows what everybody's talking about. Okay? I am not going to hold you to the names of reactions. So I will not have an example on the test where I say, which of the following is a Williamson ether synthesis? Now I may say in the question, I am using the Williamson ether synthesis to make blah, 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 and then ask you something, but you wouldn't need to know the name of the Williamson ether synthesis to answer the question. Okay. How else can we make alcohols? This is by SN2 chemistry. How else could you make an alcohol?
Coffee, hydration, coffee.
Yep, I can take an alkene. I can add water to it by acid catalyzed hydration, right? I can do that pretty easily as well, okay? And so that's where we get to the direct hydration of alkenes. You all know the mechanism, right? We take the alkene, we protonate the alkene. Which carbon atom gets the hydrogen? Whose rule is that? Markovnikov's rule. And which carbon gets the hydrogen?
The one with the more hydrogen.
Yep, the one with the more hydrogens, right? We end up in that case with a tertiary carbocation. Now the nucleophile adds, and the nucleophile of course is water. That's a fast step. And we end up with this so-called protonated alcohol as the intermediate, which then gets deprotonated to give us the alcohol plus our acid back. It's acid catalyzed. So I started with acid, I have to get my acid back. So that's acid catalyzed hydration of an alkene. Since we are involving carbocations, what do we have to be careful about? Rearrangements. So always keep that in mind. These themes are going to continue on from chapter to chapter to chapter, right? That's the thing about organic chemistry, okay? Yeah, we're going to stop there for today. Let's call it quits. We've got 4 minutes left. You all have a quiz due to me, and I want you all to turn in problem 7.26, A through C. 7.26.